The fat state, or absorptive state, is the 2 to 4 hour period after injection of a normal meal. During this period, plasma levels of glucose, amino acids, and triglycerol rise. Fasting begins if no food is ingested after the absorptive state. In the absence of food, plasma levels of glucose, amino acids, and triglycerol fall. Today, we will cover 3 topics. First, we will look at food and energy. All activities in the body depends on energy. Energy is derived from food. As we have seen this before, extraction of energy from food occurs in 4 stages. In stage 1, food is broken down to small building blocks. In stage 2, small building blocks are metabolized to form a common intermediate, acetyl-CoA. In stage 3, acetyl-CoA is broken down to carbon dioxide, and energy is conserved in high-energy compound, NADH and FADH2. Finally, high-energy compounds are oxidized. Energy is used to synthesize ATP through electron transport chain and oxidative phosphorylation. ATP is a form of circulating energy currency in cells. There's a limited amount of ATP in circulation. Most of the excess energy from diet is stored as fatty acids and glycogen. This chart shows you average energy available from major food components. For example, 1 gram of carbohydrate provides 4 kilocalories of energy when it is fully oxidized. 1 gram of protein provides the same amount of energy. 1 gram of fat provides 9 kilocalories. 1 gram of alcohol provides 7 kilocalories of energy when fully oxidized. Put them together, 9744. We should remember these numbers. Here is a question. A recommended 2,100 kilocalorie diet with 58% of calories from carbohydrate, 12% protein, and 30% fat. How much of each nutrient should one take? Since 58% of calories are derived from carbohydrate, total calories times 58% gives you calories derived from carbohydrate, which is 1,218 kilocalories. Each gram of carbohydrate provides 4 kilocalories of energy. This number divided by 4 gives you the amount of carbohydrates one should take, which is 305 grams. Using the same method, you can obtain numbers for protein and fat. This table summarizes fuel utilization in the well-fed and fasting states. In the well-fed state, most organs use glucose as fuel except cardiac muscle. In the fasting state, most organs use fatty acids as fuel except brain and red blood cells. Red blood cells do not have mitochondria that depends on glucose. Although the brain prefers glucose, during starvation, it has to use ketone bodies for some of its energy needs. Skeletal muscle and cardiac muscle can use both fatty acids and ketone bodies. The shifting metabolic patterns are regulated mainly by the insulin-glucagon ratio. Insulin and glucagon affect phosphorylation and dephosphorylation of rate-limiting enzymes, and they also control expression of target genes. Please note that in addition to insulin and glucagon, allosteric regulation also plays a role in regulating shift of fuel metabolism. Now, let's move to part 2. We will look at well-fed state. The well-fed state is the 2 to 4 hour period after a meal. Main characteristics include increase in plasma glucose, triacylglycerol, and amino acid levels. Pancreatic beta cells respond to glucose and amino acid and secrete insulin. Insulin-glucagon ratio rise. Metabolic patterns are shifted towards anabolism. Metabolic fuel is almost exclusively glucose. In the well-fed state, three major target tissues for insulin are liver, muscle, and adipose tissue. The brain and red blood cells are insensitive to insulin. Insulin promotes glycogen synthesis in the liver and in muscle. Liver converts excess glucose to fatty acids and TAGs. Insulin promotes TAG synthesis in adipose tissue and protein synthesis in the muscle. Insulin also promotes glucose entry into muscle and adipose tissues. This information is summarized in this slide. In the well-fed state, liver extracts excess glucose and uses it to replenish its glycogen stores. Liver converts remaining glucose to acetyl-CoA and then to fatty acids. Liver then converts fatty acids to triacylglycerol and release them in the form of VLDLs. Insulin promotes both glycogen synthesis and fatty acid synthesis. In a well-fed state, adipose tissues increase their uptake of glucose using GLUT4. They convert glucose to glycerol 3-phosphate. They release fatty acids from chylomicrons and VLDLs using lipoprotein lipase. They re-esterified fatty acids for storage. Insulin promotes membrane localization of GLUT4 and activates lipoprotein lipase. Insulin also suppresses release of fatty acids from adipose tissue. In the well-fed state, skeletal muscle takes up glucose and converts it to glycogen. Skeletal muscle also takes up amino acid for protein synthesis. Insulin promotes both processes. Cardiac muscle uses fatty acids as the major fuel. Brain uses glucose as a primary fuel. It uses GLUT1 and GLUT3 for glucose uptake. In the well-fed state, most of the enzymes are in the dephosphorylated form and are active, except three. They are fructose bisphosphate phosphatase 2 or FBP2, glycogen phosphorylase, hormone-sensitive lipase, These three enzymes are dephosphorylated and inactive. These three enzymes can be summarized in one mnemonic, FGH. It represents FBP2 glycogen phosphorylase and hormone-sensitive lipase.
Now, let's move to part 3. We will look at fasting state or post-absorptive state.
In this state, there's a decrease in plasma glucose (TAG) and amino acid levels, a decrease in secretion of insulin, an increase in secretion of glucagon, an increased degradation of glycogen, TAGs, and proteins. At the same time, there's a need to maintain the glucose level to supply glucose to the brain and red blood cells. There's also a need to mobilize fatty acids from adipose tissues and synthesize ketone bodies by the liver and supply them to the whole body. At the beginning of a fast, the most abundant fuel stored in the body is the fat. In a 70-kilogram man, the fat is around 15 kilograms. The most convenient fuel, glycogen, is around 200 grams. During an overnight fast, glucagon and epinephrine levels rise, and they act on skeletal muscle, adipose tissue, and the liver. In the liver, glucagon and epinephrine stimulate glycogen degradation. Glucagon also stimulates gluconeogenesis. Epinephrine and a low level of insulin stimulate the release of amino acids from muscle and fatty acids from adipose tissue. Amino acids and fatty acids are taken up by the liver. Amino acids provide carbon skeleton, and fatty acids are oxidized to provide ATP needed for gluconeogenesis. This information is summarized in this slide. This chart indicates the source of glucose in the blood during fasting. Here are three numbers we should pay attention to: 16, 24, and 48. At 16 hours after a meal, glycogenolysis and gluconeogenesis contribute glucose equally. After this time point, gluconeogenesis contributes more glucose than glycogenolysis. At 24 hours, glycogen is almost depleted. At 48 hours, the rate of gluconeogenesis decreases. The brain has started to use ketone bodies for energy. After several weeks of fasting, the brain derives about 2/3 of the energy from ketone bodies and 1/3 from glucose. In prolonged fasting or starvation, amino acids are the primary source of gluconeogenesis and contributes 80% of glucose. But in starving obese people, the glycerol pathway contributes about 80% of glucose. Ketone bodies are important sources of energy for the peripheral tissues. In the absence of glucose, even the brain and adrenal medulla can use ketone bodies, but not free fatty acids, as an alternate fuel source. This chart represents changes in blood ketone body levels. Within the first 2 weeks of starvation, ketone body in the blood, as represented here by 3-hydroxybutyrate, increase rapidly. It still keeps rising if starvation continues. The higher concentration of ketone body, the more demand from the peripheral tissues, including muscle and the brain. During fasting, one important function of liver is to release glucose into the blood. As you have seen earlier, liver first releases glucose by glycogenolysis, followed by gluconeogenesis. During prolonged fasting, the liver converts fatty acids into ketone bodies and releases it into the blood. Cardiac muscle mainly uses free fatty acids as fuel. It also can use ketone bodies during starvation. Very similar to cardiac muscle, resting skeletal muscle uses free fatty acids as fuel during fasting. It can also use ketone bodies during starvation. During exercise, skeletal muscle can use store of glycogen and triacylglycerol. Skeletal muscle can also use blood glucose and free fatty acids as fuel. During exercise, skeletal muscle has 3 sources of energy supplied. First is phosphocreatine system, or phosphagen. It supplies energy for 8 to 10 seconds. Second, glycogen lactic acid system. It supplies energy for around 2 minutes. Third, aerobic system, including aerobic glycolysis, beta oxidation, TCA cycle, and electron transport chain. It supplies energy for unlimited time. Here are some sports that use different energy systems. For example, 100-meter dash almost entirely use phosphagen system. 800-meter dash mainly use glycogen lactic acid system. Marathon use aerobic system. This chart shows you use of carbohydrate versus fat in people with different diet during exercise. Green line represent mixed diet. Red line for high carbohydrate diet. Blue line for high fat diet. This y-axis represents percent carbohydrate usage. This y-axis represents percent fat usage. At the beginning of exercise, most of the energy is derived from carbohydrate. But by the time of exhaustion, most of energy is derived from fat. This chart shows you glycogen levels before and after exercise. By the end of exhaustive exercise, the glycogen level is 0. Glycogen level can be restored in people with high carbohydrate diet. within 2 days. But for people with high fat or high protein diet, it takes much longer to restore glycogen level back to normal. During fasting, an important function of adipose tissue is to release fatty acids. A decrease in insulin and increase in epinephrine activate hormone-sensitive lipase, which degrades TAGs and release fatty acids and glycerol. Between meals, the brain uses glucose as fuel. Only in prolonged fasting does brain use ketone body for energy. In the fasting state, most of the enzymes are in the phosphorylated form and are inactive, except 3 enzymes. We have seen these 3 enzymes earlier. Again, a mnemonic FGH may help us remember these enzymes.